All right, we're talking about local linearization today, and it's just another application of derivatives. And it's a way, basically, the idea behind local linearization is that we can estimate the value of a function by looking at the tangent line near that value and evaluating the tangent line, because a lot of times the tangent line is so much easier to evaluate than an actual graph. So an example of that would be this function. This is the sine function. You might remember that from trig. And so we know some values on the sine function. You know, like we know that pi over 2 is equal to 1. We know that it has a 0 at pi and things like that. But what if I wanted to estimate this value without a calculator? What if I wanted to estimate a value in here? Maybe a value here. Well, the idea behind local linearization is that with any curve, if we zoom in far enough, the curve starts to look like a line. And so I'll show you that. So say we're looking here at pi. We're looking at this function at pi. And we're saying we want to kind of figure out what the value of the function is really close to pi. Well, if we zoom in, do you see how it doesn't look like a curve anymore at all? It actually looks like a straight line. And so if I drew a tangent line right here at pi, if I drew the tangent line at a function or at a value that I know, that tangent line would actually touch the curve or get really, really, really close. Obviously, it can't touch in more than one spot, but it's going to get really, really close to other points on the curve. And so the idea is the tangent line is so close to the function that I might be able to just evaluate the tangent line instead of evaluating the function. So let's look at another function that might make that a little more clear. So here we've got the function x squared. So it's a parabola. And if I figured out the tangent line right here at x equals 1, well, we know the derivative of the x squared is 2x, right? So the slope at any given point is 2x. So at this point here, at 1, the slope would be 2. And so I just went ahead and I wrote the equation of the tangent line because I know that when x equals 1, y equals 1, right? So I can write the equation of the tangent line. You know, because I can find the slope at any point, but I can't write the tangent line because I don't know the y value at that point. So here's a tangent line. Let me get that a little bit thicker for you. Okay. So there's a tangent line. And you see that as we get closer, let's go ahead and zoom in. We're going to zoom in. Do you see how as we get closer, I'm going to take that off now, the curve, the blue, which is actually a curve, starts to look much more like a line. In fact, it's almost exactly like its tangent line. Do you see that as we zoom in far enough? The curve itself, you can't even tell the difference between the curve and the tangent line. So the idea of local linearization is that, you know, I might not know the value of 1.02 squared, but I do know the tangent line at 1, and I can evaluate that at 1.02 because that's a lot easier than just trying to square it, right? That's something I could do in my head or with, quick math rather than needing to do a lot more work. And so I can evaluate the value of the tangent line at 1.02. And because I'm really, really, really ultra close, see right here at x equals 1.02, that's like right here, you can't even tell the difference between the tangent line and the curve. So whatever value my tangent line has at that point, my curve is going to have a really close value as well. The y value of my curve is going to be about that. So I hope that makes a little bit of sense. Let's take a look at some examples and see how this works. Okay, so first here we have a circle, and we have the point 2, -2 is on the graph, and we want to use the equation of a tangent line passing through the point 2, -2 to approximate a y coordinate. So again, this is using something where we're going to approximate the x coordinate 2.1. And I wouldn't want to put 2.1 into my original equation and solve for y because it'd be really difficult, right? Like I'd have to square 2.1 and then I'd have to somehow find the square root and maybe factor or something. Like, it would be really complicated for me to just be like, to just plug 2.1 in here for x and solve for y. Like, I don't really know what that would be, right? But you'll see that with the tangent line, I can get really, really close. I can tell what the y coordinate on my function is at x equals 2.1. I can get really close to it. So the first thing we do is we're going to find the equation of the tangent line. Okay, so here we have this function, and the equation of the tangent line, well, an equation needs a point and it needs a slope. So the slope of the tangent line is going to be the derivative, so let's go ahead and derive that. So we get 2x plus 2y dy dx plus 2 equals 0. And then I go ahead and subtract 2, and oops, I forgot my dy dx on my 2. Okay, equals 0. There we go. So now I subtract 2x from both sides, and I get negative 2x, and then I divide both sides by 2y plus 2, and that's going to be what dy dx is. Hopefully I didn't skip too much there. And then that is going to be negative x over y plus 1. So the slope of my tangent line is negative x over y plus 1. And that would be for any point on the curve. That's the slope of my tangent line. So what is the slope when x equals 2? Well, we could say dy dx evaluated at x equals 2 is negative 2, and then we know when x equals 2, y equals negative 2, so negative 2 plus 1, which is negative 2 over negative 1, which is negative 2. Positive 2, I mean. Okay, so the slope of the tangent line is positive 2, so now we have a slope. Now we just need a point. So how would we write the equation of the tangent line? We have a slope, we need a point. So the equation of our tangent line would be y plus 2 equals 2 x minus 2. I just wrote it in point slope form by plugging in the point we know. So that's the equation of the tangent line. All right, so that tells me that I can evaluate any point on that tangent line by plugging it into here. And if I evaluated it right here at this point, you know, right at 2, we know what that is. It's going to be negative 2 because the tangent line touches the curve at that point. But what if I zoomed in really, really close and I just looked like right above that at 2.1? Now the line wouldn't be touching the circle, but it would come super close to the circle. So the value of my tangent line at 2.1 is going to be really, really close to the value of my tangent line at 2. So again, the value of my tangent line at 2.1 is going to be really, 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 really close to the value of the circle at 2.1. So if I evaluate the tangent line, then I can just, that would tell me pretty close to what the value of the circle is at that point. So let's plug in x equals 2.1 to our tangent line. So what is the value of our tangent line when x equals 2.1? Ooh, that was crazy. Okay. 2.1 minus 2. So that equals y plus 2 equals 2 times 0.1. Y plus 2 equals 0.2. Subtract 2 from both sides, and we get that y equals negative 1.8. So the value of my tangent line when x equals 2.1 is negative 1.8. And because we know that if I zoom in really, 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 really close, my tangent line and my circle are almost the same function, that the value of my circle at 2.1 is really darn close to negative 1.8. Isn't that a ton easier than trying to evaluate the actual function at that point? Because again, we'd have to like plug in 2.1, square it, and then somehow solve for y, which is going to be really difficult because y is not by itself. Okay, so now we're going to approximate 1 point at when y equals 1.9. Now we already have the tangent line when x equals 2. Sorry, I said when y equals 1.9. When x equals 1.9. We already have the tangent line when x equals 2, so we're just going to plug 1.9 into that same equation. So we're going to have y plus 2 equals 2 times 1.9 minus 2, which equals y equals, let's see, 1.9 minus 2 is negative 0.1 times 2 is negative 0.2 minus 2, so y equals negative 2.2. So, again, the value of the tangent line at 1.9 is negative 2.2, and so the chances of the value of the circle being negative 2.2 are pretty good because they're really, really close to each other. So the value of that function at 1.9 is really close to negative 2.2. All right, let's take a look at another one. This is the kind that you're going to see a lot more of, where they don't actually give you a function, because oftentimes with a function you could just evaluate the function at that point. The one we saw before you can't because you know it's got all the squares and stuff. But a lot of times you can evaluate a function, and so you're going to see more of these. So this says that my function, we don't know what the function looks like at all, but we know that when x equals 2, y equals 3. So we know that that point lies on the function somewhere. We also know that the slope when x equals 2 is negative 2. And I know that because it says the derivative when x equals 2 is negative 2. Okay, so I know the slope of the tangent line at that point is negative 2. And so I can write a tangent line. I could write the equation of a tangent line for this, right? Because I have a slope and I have a point. So let's just go ahead and write the equation of this tangent line. It would be y minus 3 equals negative 2 times x minus 2. So that's the slope of my tangent line, the equation of my tangent line. The slope is negative 2, and this is the equation of my tangent line. So this tells me every point on the tangent line. And then it says we use local linearization to approximate f of 2.01. So again, 2.01 is really, really close to 2 on the function. So it's probably going to be really, really close to the derivative. So all we do is y minus 3 equals negative 2, and we evaluate the tangent line at 2.01 and figure out what it is, and that's going to be really close to what the function is at this point. Okay, so y minus 3 equals negative 2 times 0.01, and then y minus 3 equals negative 0.02, and we add 3, and we get y equals 2.98. So the value of this function at 2.01 is really, really, really close to 2.98. Since we don't actually know the function, then it's possible that it could be just like a little bit different than that. But this approximation is a really, really good way of finding it without, you see, I did all of that without a calculator. It was so much easier than trying to evaluate an actual function. So that's linearization in a nutshell. I hope it makes some sense, and we'll practice some more in class.